Sun shining on my face, shouts to the one above for giving me another day. Graham still watching, see I'm on my way to make it to that other stage in this game I started to play.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now I'm going to tell you guys about titration, which is a common laboratory method of quantitative chemical analysis used to determine the unknown concentration of an identified analyte. And so in this case, it's the slow addition of a known concentration, this is called the titrant, to a known volume of another solution of unknown concentration, until the reaction reaches neutralization, which is often indicated by a color change. So this is the setup, and we have a burette, which allows us to slowly titrate, in this case, a base of known concentration, into a flask with an acid of unknown concentration. So this can be flipped around too, where we can titrate an acid of known concentration to a base of unknown concentration. So that can work both ways. But we have to look at this from a stoichiometric point of view, where the number of moles of the acid or base that's added, so let me just say titrant added, equals the number of moles of the sample, or what's in the flask, in this case, an acid, and this is going to be called the equivalence point, also known as the stoichiometric point. And so a really important equation you're going to see in titrations is MAVA equals MBVB, where remember, molarity is in units of moles per liter, and this is just volume in liters. And so let's think about this molarity and volume be for an acid, and this being for a base. Let's look at this scenario. We know the concentration of the base, so we know MB, the molarity of the base. We can figure out the volume of the base that's titrated into the acid, so we can measure VB. And we know the volume of the acid that we started out with in the flask. And so from there, we can calculate the concentration of the unknown acid. So this is the basics of titration. And so when we look at titrations, we plot pH curves. And this is a plot of the sample pH versus the added titrant. And so first, let's start out by looking at the titration of a strong acid and a strong base. In this example, we're looking at 0.05 liters of 0.1 molar HCl titrated with 0.1 molar NaOH. So in this case, we have 0.1 molar HCl, and we have 0.1 molar NaOH. In this case, I guess we're not trying to calculate the concentration of either. It's just showing you a pH curve, but we're just showing you what it looks like when you have a strong acid and a strong base. So since you start out with a strong acid and the pH meter is going to be in this flask, we start at a low pH value of approximately pH 1, since it's a strong acid, right? So the pH starts low, and then it gradually increases as you keep adding the base that's dripping down into the flask, and then it reaches its stoichiometric point, or the equivalence point, at pH 7, where it has this huge vertical jump to a high pH value. So the stoichiometric or equivalence point is at pH 7 because the number of moles of acid that was added is equal to the number of moles of the hydroxide ions in solution. The products such as NaCl or water does not affect pH. So salts and water do not affect the pH value. And so, on the other hand, if the sample was a strong base, so we're flipping this around, and you start out with a base here and an acid up here, then the pH curve would just look the opposite. We start out at a high pH value, and then at the equivalence point, it would have this huge jump again, all the way down, and then we would end up at a lower pH value, since after the equivalence point, you now have a more acidic solution. So now as a second example, let's look at the titrations of a strong base with a weak acid instead of a strong base with a strong acid. So now since the sample is a weak acid, the pH starts at a low value, but slightly higher than when we had a strong acid. So when it reaches the stoichiometric or equivalence point, at a point above pH 7, and then it ends at a higher pH. So this pH value is going to be greater than 7. So an example in this case is sodium hydroxide, which is a strong base, and acetic acid, which is a weak acid. The reason why the stoichiometric point is above a pH value of 7 is because the number of moles of base added has to equal the number of moles of acid in the sample. And the products are, in this case, sodium plus, CH3, COO minus, and H2O. And this anion that is a product of this reaction is a base. So the strong base basically dominates the weak acid and therefore shifts the stoichiometric point to a pH above 7. So before the stoichiometric point, the equilibrium for an acidic solution would have been, let me draw it up right here, CH3, COOH, aqueous, plus water, goes to H3O plus, plus CH3, COO minus. So then we know how to write out the Ka, right? It's going to be H3O plus, CH3, COO minus, over CH3, COOH, not including water. So when the acetic acid concentration is equal to the concentration of the conjugate base, then we're going to get point C, which is right here. Then Ka is the concentration of the hydronium ion. Since these two concentrations are equal, I can cancel them out, and taking the negative log would give us pKa equals pH, which is going to give us the equivalence point. So this is a way in which we can calculate the equivalence point when we titrate a strong base with a weak acid. Basically, we equivalate the acetic acid concentration to its conjugate base so that Ka equals the hydronium ion concentration. Again, the reason why the pH is greater than 7 is because the strong base dominates a weak acid. So now let's look at another scenario where you titrate a strong acid with a weak base. And coming from this example, you probably know that the strong acid is going to dominate it, right? But as an example, this is adding HCl, which is a strong acid, to ammonia, which is a weak base. And so let's write out that equation right here. We have NH3 plus HCl plus water goes to the ammonium ion plus Cl minus plus water. So since the sample is a weak base, the pH starts high, it reaches a stoichiometric point that is now below 7 and ends at a low pH value. So in this case, ammonium chloride is the salt formed and NH4 plus is acidic. It's the conjugate acid to the ammonium. And so since this is acidic, the strong acid dominates the weak base, and the pH value is going to be less than 7 for the stoichiometric or equivalence point. So before the stoichiometric point, the equilibrium for a basic solution, let's write this out again. So NH3 plus H2O going to NH4 plus, this is the simplified version, OH minus, Kb, or the basic constant, is going to be NH4 plus, OH minus, over the reactant, NH3. And so when the concentration of NH3 equals the concentration of NH4 plus, then we're going to get Kb equals the hydroxide concentration. And again, taking the negative log of both sides is going to give us pKb equals POH. And remember, POH is 14 minus pH. And so as you can see, depending on whether we titrate with a strong acid and a strong base, or a strong base with a weak acid, a strong acid with a weak base, the titration curves are slightly shifted, and the equivalence point is going to get shifted from the neutralization point that is a neutral pH of 7. And so just make sure you understand that based upon what acid and what base you're mixing or titrating, you're going to end up with a different curve.
Loose like you sipping on some moonshine mix. No time to care about what the fools might think. Only focused on fam and doing my thing, brother. No holding back, can't lose my